Welcome to Microsoft Build 2017. Good morning, or good evening, or happy midnight, wherever you happen to be. My name is Simon Tao, and I'm a program manager on the Windows graphics team. I'm here to talk to you today, all of you DirectX developers out there who are building graphically rich user experiences. You may have heard of this HDR buzzword, and you're probably wondering, what does it all mean? And does it have anything for me and my app? Well, the Windows 10 Creators Update unleashes HDR and advanced color, and it helps you build the next generation of graphically rich user experiences. The first part of this video will give a recap of some key terms and concepts in color, and go over why we think advanced color is so compelling for users. The second part of this video will be a deep dive into how you can light this up in your DirectX app. So some of you may already be familiar with terms like 4K, UHD, and HDR, but you probably have never heard of advanced color. What am I talking about? Advanced color is a term that we use to describe a new kind of visual content, and it has one of three major improvements to visual fidelity: better dynamic range, better color gamut, and better precision. And an advanced color device is anyone that can reproduce this kind of content while preserving that improved visual fidelity. Okay, Simon, so you've just traded one piece of jargon for three. So let's look at what each of these things means. Higher dynamic range. This is all about the difference between the brightest points in a scene and the darkest points, and also all of the color values in between. Now, when we talk about brightness or luminance, we typically use a unit called nits. And for reference, the studio environment that I'm standing in is right now around a couple hundred nits in brightness. And a typical high-quality SDR monitor, standard dynamic range monitor, peaks out at around 500 nits. Well, what about the real world? Well, let's pretend that we're on this beautiful beach and we're looking at the sunset. So if you look at the shadows, it'll be around 1 nit. But looking at the sun's reflection off of that van, you get to around 10,000 nits. And if you stare directly at the sun, don't do this at home, kids, you're talking about millions to even billions of nits. So it's clear that we're losing out on so much of this real dynamic range when viewing this content on a standard SDR display. Wider color gamut. This is all about more saturated hues and colors. So on the left, we have the spectral locus, and this is a representation of every color that is visible to the human eye. So how many of these colors can you get on an SDR display? This many. sRGB is the most common color space supported by SDR panels, and you lose almost 2/3 of the human visible colors on such a display. And finally, we have high precision. Now, this is all about reducing banding, or that kind of stair-step effect you see when you're looking at a smooth gradient, such as this picture of that blue sky. Now, I've exaggerated the effect of banding on the left, and the 8-bit per channel side, which represents an SDR display quality, doesn't look too bad. But depending on the scenario, the human eye actually needs at least 10 to 12 bits of precision to completely eliminate banding. All right, so let's take a look at this in action. Now, you're probably viewing this talk on a standard dynamic range monitor. And unfortunately, the geniuses at Microsoft Research haven't quite figured out how to beam or teleport an HDR television into your living room or office. So we're going to do the next best thing. I'm going to ask you to use your imaginations for a bit. And I'm going to show you a pre-recorded video that we took in our offices in Redmond. The Unreal Engine is a very popular video game engine. And we've taken it and modified the Infiltrator tech demo to use advanced color. Now, obviously, looking at this video over the web, you're not going to get anything close to the real visual quality of being here in person and seeing the actual HDR television in person. Instead, I want you to look at the relative difference between the SDR and HDR versions, especially the contrast and saturation. And spoiler alert, the HDR version is on the right side. So in summary, an advanced color display supports at least one of these visual fidelity improvements. And as a rough guideline, as a developer, you can expect that an advanced color display generally supports at least these minimum performance metrics. Now, hold on a second, Simon. You haven't mentioned frame rate or resolution at all. Don't the terms UHD, ultra high def, or 4K mean anything? So trust us, we are the DirectX team, and we do love our pixels and frames per second. But Windows is agnostic to these factors. For example, if you're playing a UHD movie at 24 frames per second, or you're running a video game at 1080p resolution, we won't restrict you in any way. So we think that this kind of new display and new content that's coming over the next couple of years will represent a generational leap in visual fidelity. Long term, we think that every device, every piece of digital content, and every app will eventually support advanced color. But in the immediate time frame, we think there are a few areas where consumers have demonstrated a lot of excitement for advanced color already. And therefore, this is where you get the most opportunity as a developer. First are movies and videos. So there is a lot of HDR movie and video content available publicly right now. If you've used online streaming services or you have UHD Blu-rays. Video games are a great example because many modern video game engines, such as Unreal that we showed before, already render in HDR internally. What they do is they physically simulate the full quality of the entire game scene, but at the very end of the pipeline, they downconvert to an SDR panel. And finally, we have creative apps. These are the photo and video editors and drawing apps, for example. Now, if you've ever used a DSLR camera and you've worked with raw photography, you probably know that modern camera sensors are already far superior to traditional SDR displays. They get 10 to 12 bits of precision, they have more f-stops, which is essentially dynamic range, and they're wide gamut. So just like video games, this is a case where there's existing content out there that's just going to look better on an advanced color display. All right, you're excited and ready to build an app. What do you need to get started? First, you're going to need the Windows 10 Creators Update. In terms of hardware, you're going to need an HDR10 capable display and a high-end discrete graphics card and the latest graphics driver. Once you have the right configuration, Windows will automatically light up this display, will automatically light up advanced color on that display. But you can easily turn it off in the Settings app. Now, I want to call out that these are pretty high-end system requirements. One of our top priorities in upcoming releases of Windows is to lower these requirements and increase the reach, the addressable market for advanced color. First, we want to support premium displays that are wide gamut and high bit depth, but not HDR10. Second, we want to support integrated GPUs and more mobile form factors, including laptops. And of course, we're always working on perf and power optimizations. All right, once you have the right configuration, you can use these APIs. The good old DirectX family, and this is, of course, what I'm going to focus on in this video. And their cousins, the WinRT APIs Win2D and the Visual Layer APIs. If you use XAML, you can play back video and use DirectX with the swap chain panel control. And if you're on the web platform, you can use the video tag. So of course, there are some things that are missing from this list. Our strategy is to first build the foundational low-level components of the platform and build up from there. So expect this list to grow over time. And of course, we're always looking for your feedback as to what capabilities that you need in your apps. Great. Now's the part that you've been waiting for, lighting things up in DirectX. So all of the code samples and reference documentation that I talk about here, I'll have links to at the end of this video. Let's go over a couple pieces of terminology first. You're probably familiar with pixel format, how your numbers are laid out in memory. Now, what about color space? So if you have a bunch of data, color data, in that pixel format above, what is the actual color? What are the actual photons that are coming out of your display? Now, this essentially is what color space is. It defines this relationship between numbers to real colors. So for example, you take this RGB triplet. The fact that it is that particular shade of blue is only because it is defined within the sRGB color space. And don't worry, I can assure you that this is an officially approved color in the Build 2017 color palette. All right, our first recommendation. Use an advanced color pixel format and color space. In short, if you're used to using BGRA 8 and sRGB for your standard dynamic range content, this just doesn't provide enough precision or range to accurately represent advanced color content. Instead, depending on your scenario, we recommend one of two options. First is half precision floating point and the sCRGB color space. And second is UINT 10-10-10-2 plus the HDR10 color space. And below are our typically wonderful and verbose DXGI enum values. Option 1. You should default to this choice as it is very flexible, although it may not always be the most optimized one. Because we're using floating point, we can basically represent any color possible. This includes going up to millions of nits of brightness, and even imaginary colors that a typical human can't perceive. However, it is twice the memory and bandwidth consumption. It is 64 bits per pixel, so it's twice the cost versus an SDR RGB8 texture. So I want to focus on this last point. As you know, we're using a different color space to render advanced color content. This is a much bigger change than simply switching a pixel format. So if you have RGB8 data and you switched it to RGBA16, you basically just get additional precision. Alternatively, if you switch to R8, you're just converting to like monochrome rendering. However, if you go from sRGB to sCRGB or HDR10, you're completely changing the meaning of what each color means. So for example, that blue patch that we saw a couple slides ago, that will be a completely different color. And all of your pixel shader math is going to be wrong and will need to be updated. So unfortunately, it'll take us too much time to go into all the specific details about how the math changes with each color space. Fortunately, HDR10 and sCRGB are pretty standard and well understood. So there's a wealth of great guidance online on how to convert your math and how to think about the numerical values that you'll see. Option 2. This is best used for specific use cases. So if you think your app is primarily going to be used in full screen scenarios and fill the entire screen, this includes video games or media players, option 2 can improve your performance. First, it consumes less memory than option 1, but also HDR10 is the standard color space for transmitting HDR content over DisplayPort and HDMI, and is also used for storing a lot of HDR video. So in the case of, in the full screen app case, the GPU sometimes can optimize, for example, by directly copying the HDR10 content and sending it out over the wire without needing any conversions. On the other hand, this option just doesn't have enough precision to properly handle semi-transparent blending, or if you're going to use it as an intermediate and repeatedly render to the same texture. And finally, 10-10-10-2 is not supported by Direct2D or Win2D. They only support FP16. All right, so let's take a look at this in code. For clarity, in all of my code samples, I've eliminated any error handling and also simplified API calls that aren't directly related to advanced color. So first, you want to create a swap chain descriptor like normal, but you should choose one of the recommended pixel formats, either FP16 in this example or 10-10-10-2. Go ahead and create your swap chain normally, and then query interface for IDXGI swap chain 4. This interface has the new method setColorSpace1, and this is where you pass in the color space that you're using, sCRGB in this example, or HDR10. Now, you may notice that all these APIs are swap chain specific. So we've put requirements on your swap chain because this is where you pass your rendered data to the operating system. And the OS needs to understand how to interpret your surface. Within your app's rendering pipeline, so intermediate surfaces or shader resource views and other things, you have a lot more flexibility. You can choose a pixel format and color space to meet your requirements. The only thing is that you need to convert to one of these two options at the end of your pipeline. Second, you should adapt your app to the display's color performance. In this case, when I talk about display performance, I simply mean what is the dynamic range, what is the color gamut, and what is the precision of your display. Now, why do you need to care about this? So it's important to understand there's no such thing as an advanced color only application. Whether you're Win32 or UWP, users are going to be running your apps on literally all kinds of displays of all shapes and sizes, from high-end HDR televisions to inexpensive laptops and tablets. So gamut and peak luminance are already going to vary today by hundreds of %, and this diversity is only going to grow over time. Next, even a particular display can change at any time. The user could unplug the monitor, they could adjust the backlight, or they could go into a low-power device state. So therefore, we recommend that whenever possible, your app should render at full quality and then gracefully handle when that display doesn't meet your app's expectations. So let's take a look at a more concrete example. This is a highly simplified view of a typical DirectX application rendering pipeline. You start with some visual assets, you perform some rendering, and then you just present it to the display. Let's imagine that you are building a fancy new Paint app that uses advanced color content. So in this case, your visual assets would be the color brushes that the user can select. Your rendering would consist of the geometry of those ink strokes, and you present your swap chain to the display like normal. So ideally, you would allow the user to select any possible color. So that is any human visible gamut, and any human visible luminance. But at the very least, you shouldn't arbitrarily restrict them to any color space. For example, saying you can only choose sRGB colors just because. Instead, what you should do is you should check for the display's color capabilities. And based on those capabilities, perform some specific optimizations. For example, on the asset on the input side, let's say this display really only supports the sRGB gamut. So one option you have is to restrict the user to only colors, to only paint colors that are in sRGB, only colors that are actually renderable on the display. An alternative is to say, no, I'm actually going to let the user select any visible color, but on the output side on the right, I'm going to tone map to adapt to the sRGB gamut. So the advantage of this approach is that, let's say the user then saves their file, and next year they go and upgrade their monitor, let's say to one that supports the DCI-P3 gamut, which is wider than sRGB. When they run their app again, suddenly this existing drawing that they have is going to look much better on the display because you've chosen to adapt at runtime specifically to the display's performance. So the way we want you to detect display performance is also through DXGI. Respond to changes in the display color state by checking if your DXGI factory is current and recreating if necessary. From your swap chain, get the DXGI output and use our friend query interface for IDXGI output 6. This interface contains the new method and lets you get the new DXGI output desk1 struct. And so this is the struct that contains all of the key numbers that we care about. So once you get the struct from here, your app should check about the performance parameters that it cares about. If you need high precision, you should check the bit depth. If you're that Paint app, you should check the color gamut of the display. And the primary values here are defined in the XY coordinate system. So that is a standard representation of colors that is independent of luminance. If you are building a video game that wants to render a spectacular explosion, maybe you need to know what the peak luminance available on that display is. Here, max luminance and max full frame luminance are two distinct concepts. So many HDR displays, they support rendering extremely bright colors, but perhaps only in a small spatial portion of the display, let's say 10%. Meanwhile, if you try to fill the whole screen with peak white, you're only going to get the value filled out in max full frame luminance. Now, in some cases, your app may not care about the specific display performance metrics. And all you need to know is, hey, am I rendering in HDR at all? So in that case, you can check the color space type. Our last topic is image assets. You have a few options depending on your needs. If you need highly runtime optimized texture format for your assets, you should consider using the BC6H compression method for DDS. BC6H supports half float, half precision float, and it is natively supported on all modern GPU hardware. If you're going to produce user-visible images, we recommend JPEG XR. JXR is fully supported on every Windows device. And just like BC6H, it supports floating point values. It actually supports basically floating point going up to at least 32-bit per channel single precision. In addition, it supports alpha and an optional lossless compression mode. Finally, JXR offers a limited form of backwards compatibility with SDR displays. So if you're rendering a floating point JPEG XR and you're doing it on a normal 8-bit SDR panel, all the colors within the sRGB color range, color gamut, sorry, they will appear as normal. And all colors outside of sRGB will be numerically clamped. OpenEXR is a very popular professional HDR format. And even good old 8-bit JPEGs, when paired with the right ICC profile, are suitable for representing wide color gamut data. And in fact, many cameras today are already producing this kind of JPEG. So in addition to these options which are available today, Microsoft is working with industry groups such as MPEG to define future-looking and cross-platform HDR image still format. In the interest of time, I'm only going to show you a code snippet that loads JPEG XR using the Windows imaging component. You start with your file stream, and then you construct a WIC decoder and WIC frame as normal. Next, we explicitly convert to the FP16 pixel format using a format converter. And finally, we initialize a Direct2D image source, which can then be used as an input to Direct2D. So this chain of code is essentially identical to loading SDR image assets, except we have specified the HDR pixel format. In WIC, unlike in DirectX, the notion of color space is baked into the pixel format. So I want to give a plug for the excellent DirectX Text texture library, which is written by my colleague Chuck Walburn. So DirectX Text, this library is fully open source and supports loading every image format that I listed on the previous page. And you can find a link to it at the end of this video. Great. So what have we learned today? Now, hopefully you've been convinced that advanced color displays are awesome, and maybe your friend isn't so crazy for raving about their new HDR television. You're going to need to get your own display and GPU to take advantage of this. But once you do, you can unlock amazing new color experiences in both your new and existing DirectX applications. You will need to think about color in more ways than you've probably done before. But this is well worth it to ensure that your app can scale to present and future displays. And with that, I want to thank you for spending your time to watch this video. I hope that you've learned something about advanced color today, and you've gotten some inspiration to build the next generation of awesome graphics experiences. Thank you very much.